Okay, guys, let's do a word problem with vectors. We've learned a lot about vectors already. How are they useful? Well, if you're in a physics class, you will probably already know that vectors are really useful when it comes to classical mechanics. When you're dealing with speeds and forces and different things, it's really helpful to use vectors to describe the direction and the velocity, the force at which something is moving. So let's do one here. Let's suppose that we've got a boat in the water, and I'll just draw that boat from the origin. Let's suppose that boat is moving in a certain direction. It's got a motor on the back of it. And let's suppose it's moving, let's suppose 50 degrees. Suppose this angle here is 50 degrees. Let's call this east, north, south, and west. We're looking bird's eye view down on the boat. It's moving 50 degrees. Let's suppose that motor is moving it at 15 miles an hour. Okay, so we have a vector that can describe the speed and direction of our boat. It's moving 15 miles an hour, 15 degrees north of east. Okay, now this is the nice thing about vectors. This magnitude right here, this 15, while it is the length of our vector on the plane, it represents a speed in real life. And in real life, it won't just represent a speed. Sometimes it can represent a force as well. Right? You can have a force vector also. Those of you in physics know this. Okay? Of course, we could look at the x and y components of this vector, and we actually will in a second to solve the problem. Okay? This is all well and good, but what if there's some outside force acting on this boat? So let's suppose that the motor isn't the only thing influencing the speed and direction of the boat. Let's suppose that this boat is actually in a river. Okay? Maybe a really wide river, and that river has a current, and that current is flowing in this direction. Okay, so we've got a current pushing our boat. Let's suppose the current, I'm going to represent the current with a vector over here. That vector is still going to be from the origin, but let's suppose that vector is, we don't need to be that long, maybe that long. Maybe this current is moving 6 miles an hour, and it's moving in the direction, what angle does that look like? Maybe 170 degrees from our 0 over here. East is 0 degrees, so maybe that's 170 degrees there. Okay, so here's what we want to know. The motor is pushing the boat 15 miles an hour in this direction, 50 degrees. The water is pushing the boat 6 miles an hour in this direction, 170 degrees. Okay, what we want to know is, where's the boat actually moving now? Okay, it's not moving in this direction because the water is pushing it off that course. It's not moving in this direction anymore because the motor is still pushing it in this direction. Okay, and also, what speed is it going? Where is it going and what speed is it going? Okay, the big idea here is that we can figure out the resulting speed and direction of the boat by adding these two vectors together. Okay, that's why adding and subtracting vectors is so nice, because we can figure out the resulting behavior of an object that's moving. Okay, in simple situations like this. Of course, if there was some other vector, maybe there's also wind pushing this boat, or people are in the boat paddling, there's more vectors that might be acting upon this boat, and we would just add those vectors in as well. Okay, so remember, when we add vectors together, that's like taking the tail end of one vector. So let's give these vectors names. We'll call this vector B for the boat, and we'll call this vector C for the current of the water moving it. Okay, so when we take B plus C, remember how we look at that geometrically? We did that a few videos ago. You take the tail end of one vector and you move that vector, you shift it over so that the tail end of that vector is on the same point as the tip of the other vector. Okay, so I'm going to take this vector C, this guy, and I'm going to move it and shift him over so that we have our vector C is there. Okay, so I just kind of took this thing and moved it over there. Now, if I go from where my boat is to that resulting point, this vector right here, this guy, that is our resulting speed and direction of our boat. So if I can figure out the angle of this resulting sum vector, this is C plus B, and if I can figure out the magnitude, that will tell me how fast my boat is moving and what direction it's going. Okay? So let's add these two vectors together. I'll move over here I've made kind of a mess here, so I will move to my graph paper here. Okay, so again, here's our boat vector moving 50 degrees, and it is moving, let's see, 15 miles an hour, we said, right? So I'll write that magnitude. And our wind is pushing us 170 degrees this direction, and that's going 6 miles per hour. And we want to add our vector B plus our vector C. Okay, well, I think that you see the issue here is in order to add B plus C, we need the components of B and C. So we need the x component of B and the x component of C, and we'll add those together to get the x component of our resulting vector. Okay, so let's work on that. Let's first work on getting the x and y components of B. Okay, well, the x component of B is right here, and the y component of B is right here. So I'll just call this B sub x, and I'll call this B sub y. So B sub x is the x component. We know how to find B sub x because we know that we have the hypotenuse of our 50-degree angle, 15, and B sub x is the adjacent. So I know that the cosine of 50 will give me B sub x over 15, which means that B sub x is just 15 times the cosine of 50. And the same thing for B sub y. Sine of 50 equals opposite hypotenuse B sub y over 15. So I know that B sub y equals 15 times the sine of 50. So this is my x component and this is my y component. We'll just go to our calculator and we'll calculate those. What do I got here? 15 times cosine of 50, and I got 15 times the sine of 50. Okay, so there's my values. I'll just put them in here. I'll just round them. Okay, I'll round them as 9.64 for x and 11.49 for y. Okay, now of course you could use more digits if you wanted to be more precise, or if you wanted to be super precise, remember you just hit store. You pick some value, some letter. So since this is the y component, maybe I'll do alpha y. Y is there. And then anytime I need that value, now y is that value. So anytime we did this when we did the trig star, I showed you guys this. So y, I have all those decimal places, so I can be more precise that way. But we'll just write this down for now. This is good enough for this example. Okay, and I think on the quizzes it tells you to use just 2 decimal places and stuff like that. So there's my x and y components of B. That's this value and that's that value, 9.64 and 11.49. Okay. Let's also do the same thing for C so we can add those together. I want to know CY and I want to know CX, those 2 values over there. Let's do that. Do I have space? I guess I can sneak that in here. I might just I'm going to skip this step and just see, okay, well, it's pretty obvious that C sub x is cosine of 170 times 6. Okay, same way we set up our SOHCAHTOA equation. Cosine 170 would equal C sub x over 6. We'd multiply both sides by 6 and we'd get this. And but for the same reason, we know C sub y is 6, which is our hypotenuse, times the sine of 170. Okay, and those are both things. Since this angle isn't on my unit circle, I'm just going to go ahead and go with my calculator. So I got 6 times the cosine of 170, and I got 6 times the sine of 170. Now hopefully notice we have a negative there. That's the x value. Do I have a negative x value? Yes, I do. So it makes sense that my x is negative 5.9. So negative 5.91. That's rounded, and then positive 1.04. Good. So we now have the boat motor vector in component form right here, and we have the current of the river in component form right here. So what do we do to get the resulting behavior of the boat? We add these vectors together because both of those vectors are acting on the boat right now. Okay, so we take B and we add C. Okay, so we just need to take our 9.64, which is our x coordinate of B, and our negative 5.91, which is x coordinate of C, and add those together. 9.64, negative 5.91. 91, 3.73, and we'll do 11.49 plus 1.04. These are for the y coordinate there. We get 12.53. So I could try to graph that, but I see that I'm going in the positive x direction 3.73 and in the positive y direction 12.53. So I'm probably doing something like this. This is the resulting action of my boat. It's going 15 miles an hour in that direction via the motor. It's going 6 miles an hour in that direction via the river. And so when those two forces act together, we're moving on this vector here. Now what we want to know is, what is the angle of this vector and what is the magnitude of this vector? Okay, that's what we want. We want the angle and the magnitude, and we've already learned how to do this. Given the component form, how do you find the angle and the magnitude? And let's do that on this page here. Okay, I'm running out of space, so we'll just draw another picture here. Here's our vector, c plus b, and we know that it has this form, or this is its component form, 3.73, 12.53. Okay, so its x coordinate, or its x component, excuse me, 3.73, and its y component is 12.53. We want to know theta, and we want to know magnitude. Okay, what direction is it going? That's theta. And how fast is it going? That's our magnitude, or our hypotenuse. Okay, we know that it's going this fast in the x direction, 3.73 miles an hour. We know it's going this fast in the y direction, 12.53 miles an hour. How fast is it going in our new direction, theta? Okay, well, we know that we can find theta by taking the inverse tangent of our opposite over our adjacent. Okay, remember, to find an angle, you can use the inverse tangent of the ratio, the tangent ratio. Okay, so I can ask my calculator for that. Inverse tangent of 12.53 over 3.73, 73.42. Does that seem about right? Yeah, that looks like about a 70-degree angle. Sure, I believe that. So 73.4 degrees. My boat is going in that direction. Okay, and then we can, what are we doing next? Oh, we need the magnitude. How do we find the magnitude again? I want to find the magnitude of c plus b. How do we do that? Oh, duh, Pythagorean theorem. It's going to be the square root of 3.73 squared plus 12.53 squared. Okay, and that's easy enough to do. Square root of 3.73 squared plus 12.53 squared. 13.07 miles per hour. So, look back here. We have just figured out the resulting vector of our boat. We know that it is going 13.07 miles an hour in that direction, and we know that the angle is 73.4 degrees. Okay? This exact same process could be used if these were forces. Okay? Maybe these aren't speeds, maybe they're forces like 5 newtons and 7 newtons. I took a peek at your quiz, and some of you on your quiz is going to be a force rather than a speed. So when you get to your quiz, if you see like, oh, newtons, don't be scared, or pounds or whatever, you just treat that as the magnitude of the vector and you follow these same steps. Okay, so I hope that was clear, guys. Again, that sums up this section, the first series of videos. I'll put these in a playlist there on YouTube. So I hope this helps. See me on Zoom, the office hours there, if you need additional help or explanation or clarification, guys. This is my first time teaching this kind of stuff, so your feedback is really valuable to me. Okay, anyway, bye for now.